Welcome to part 2 of our electromagnetic radiation waves lecture or lesson for this unit in AP Chem. We are going to be getting into part 2 this time. I hope that you guys had success with your practice calculation and your homework problems. If you find that you're running into any problems, please make sure that you come into a Google Meet. Those are optional. They're there to help you if you need them. They're not mandatory. So if you want to come in, you can and get some help. Otherwise, use that time to work on another class. But like I said, today we're going to be getting into part 2. Now, part 2 and part 3 are going to talk about specific ways that we can use electromagnetic radiation to probe the insides of atoms to see what's going on. And line emission spectroscopy or line emission spectrums are one of the earlier ways that scientists were able to kind of figure out what was going on inside the atom. Scientists originally had the idea that you have this kind of atom as a ball theory and that it's solid in the middle. And then they started talking about these things called electrons and protons, and they didn't initially kind of know how they looked. So they kind of latched on something called the plum pudding model developed by a scientist named J.J. Thomson. That was where you had negative charges, kind of like a chocolate chip cookie, like the chocolate chips in a cookie almost, and then this sea of positive charge. So that was the plum pudding model, and that didn't work because eventually a guy named Ernest Rutherford shot a bunch of particles at gold atoms and realized that there was this center. So slowly scientists went from the idea that there's this solid ball to this positive center with this negative area around the outside. And so line emission spectroscopy actually is one of the first things that gives us evidence to the structure on the interior of your atom as far as electrons go. So it's really important, and it's actually pretty easy to figure out now. Obviously at the time it was tricky, but right now we kind of got the hint. So the general idea that we find with all of these techniques to probe and poke on the inside of the atom is that we find that if you can add energy to atoms, so you can add it by either adding electricity or some form of electromagnetic radiation, you can actually cause parts of the atom to either completely leave the atom or they can change their position in the atom. So we can make the atoms move too, we can make them flex and stretch and rotate. We can do all these different things. And then seeing how that particular atom responds to the energy that you add to it through that electricity or electromagnetic radiation, what we can do then, looking at its response and the data that it gives back, we can actually use the numbers we get back from that to figure out what's going on inside of there. And like I said, the easiest technique that they actually did to start off with is they heated up the samples or got the samples all hot and bothered by adding electricity to them. So what happens is you take a gas sample and you put it in this really skinny tube and then you apply electricity to it. Now, if we were in the classroom, we would be taking a look at those together and doing these calculations. Unfortunately, that's not the case right now. So we're going to be taking a look at what that kind of looks like on the screen here. So what you guys are actually seeing here, this is the setup that I would have in my class. So it is a tube with kind of these metal brackets on the end of them. And then inside you have a sample generally of a pure elemental gas. I have neon, nitrogen, oxygen, hydrogen, krypton, helium, all those kinds of things. And so what you do is you put that tube into this little box. The box allows electricity to run through it. You turn the light on, you turn the box on, which makes the light glow right here, and then you turn the lights out in the room. And so what you see, this is a tube of hydrogen gas. What you would see if you take that tube of hydrogen gas is you'd see kind of a bluish, reddish glow. Excuse me. It looks really cool. And you're like, oh, wow, fun party trick. However, the real party trick comes in when you take this prism, and the prism looks different. You can either use something that's called a diffraction grating. It's a little like cardboard thing that's got, it almost looks like rainbowy on it, or you hold up, it's called a spectroscope, and it's a little piece of black plastic with that same kind of special sheeting in it. And I'll show you what the sheeting does in just a second. So when you take a look at the light sample, the light source, through this little prism or this grating that you have, you end up, instead of seeing this whole tube of one color of light, you actually get this pattern down here, which is called a line emission spectrum. So you will actually see one red line, one very bright blue line, and then some kind of more faint blue lines towards the end of the spectrum, or towards the edge of what you can see. And so this is the line emission spectrum for hydrogen. And you ask yourself, how in the world does that actually work? So here is what happens. Imagine your face is over here, okay? Looking through, there's your eyeball over on the right side of the screen here. So I have this gas tube that has hydrogen in it. And then what you do is you put the little grating right here by your eyeball, okay? So we've got the eyeball there. That grating acts as something called a prism. And one of the things that prisms are able to do is they are able to bend light. And the way, or the amount that they bend light, is dependent upon the wavelength of that light. So if you think about the light from the gas tube, the little thing you'd end up holding up to your eye, that grating, or the little spectroscope that you hold up to your eye, what that does is it splits the one color of light that's coming from the particular tube, and then it actually takes it, it hits the prism, and then it bends it for all of the different colors of light that make up that particular sample. Normal light, if you would hold it under the diffraction grating, looks like a big rainbow because you can see all of the different parts of the visible spectrum. The visible spectrum, again, is the type of light that we can see. It's red, orange, yellow, green, blue, and purple. And so what ends up happening is that if you look at pure white light, you get this beautiful solid rainbow. And when it appears to your eye, it looks like white light. So it looks like nothing. It's just the light that you're used to. But what happens is when we go back and we take a look at a sample of gas in like a hydrogen tube here, that light is composed of not all the different colors of light, but instead very distinct wavelengths of light that when you add them up, give them this kind of purpley glow. And so in the case of hydrogen, what we can do is we can figure out the different types of light that make it up by taking the prism and splitting the different wavelengths apart. So in the case of hydrogen gas, what ends up happening is the red light we split, and the red light has a wavelength of 656.3 nanometers. The bright blue band that you see is 486.1 nanometers. The bluer, kind of indigo almost band is 434.1 nanometers. And then the purple that you see is around 410 nanometers. So that purplish light back here is composed of all of these different types of light. Now, there were a couple more bands that you saw here, but we only really take a look at the strongest, most distinct bands when we're talking about these spectrums. And so this is actually kind of like a fingerprint for an element. Only hydrogen will produce a spectrum like this. It's its own unique thing. Here are, I'm going to quick skip ahead. Here are a couple other spectrums that you see when you look at different types of light. So here's the spectrum for hydrogen. Like I said, there are those bands that you kind of see a little bit. Helium, on the other hand, looks like this. It's its own distinct thing, like it's its own unique thing. It's like its fingerprint. It's actually kind of interesting. They used to think that the sun was made of hydrogen. So they used to think that it fueled itself by consuming hydrogen. However, when they looked at the sun using one of those spectroscopes and then split the light, they got this band here. And that's actually how they discovered that the sun had helium in it instead. So it gave us a completely different chemical signature. And so you get a really different look. Now, helium, visible to the eye when you heat it up, has kind of a purpley pinky glow to it. But when you put it under the spectrum, you get all of these different lines. Neon has this very bright kind of red distinct structure. Sodium looks like this, and Mercury looks like this. And we could go on and on and on, but every element has its own unique line spectrum that lets us know that it's that particular element. So if you were trying to do an analysis and figure it out, one of the ways you could see if it's a specific element is actually by taking that element, and you could even heat it up in like a flame. And then if you look at the flame with your spectroscope, you sometimes can see the lines and it confirms that it's that particular thing. Now you ask yourself, how in the world are those lines formed in the first place? How do we even get light? So the general way that you get light formed when you run electricity through it is because we are causing excitations of electrons. So if you remember with our electrons, you got the nucleus in the middle, and then you've got your kind of layers of electrons for your energy levels, if you remember the terminology. What ends up happening is when you run electricity through a sample of an element, it creates extra energy within the atom that takes electrons and it actually promotes them up to a higher energy level than they previously were at. So if I think about an electron maybe at the 1s level in hydrogen, because that's all it's got is a 1s1 electron. If I add electricity, I can maybe take my 1s electron and bump it up to the 2s shell, or the 3s shell, or the 2p, or any of those. And so what happens is when they move up to those shells, they are in what we call an excited state. It means that it's not its normal state of being because it has extra electrons. And that's great, and those electrons can remain at that excited state, but eventually, as time goes on, those electrons lose their oomph, essentially, and they fall back down to their original level. So kind of in this picture, you can see we have this electron that's dropping down. So I've added energy to make that electron go up. I lose that identical amount of energy when the electron falls back down. And when that electron falls back down, it releases that energy in the form of a photon. Now, a photon is essentially a particle of light. And so when we take a look at that light sample that you guys are seeing here, that light sample is actually coming from all of those electrons that have been excited. When they fall back down, they release their light, and that's where you get your light from in the first place. So that is what causes that transition, okay? Now you say to yourself, hey, there's different colors of light, and that is totally true. So what ends up happening is that depending on the size of the jump that happens, you get either a lower or higher wavelength of light. And generally, the way that it works is that smaller transitions, so let's say maybe a jump from the 1s electron to the 2p shell, that's a pretty small jump that happens. That will give us a different colored light or different colored photon or different size wavelength photon coming out than if I go from the 1s to the 4p shell. Okay, and so in this particular picture that we have here, it kind of shows us the different types of wavelengths that come out for our transitions. So if I have an electron that's sitting in the second energy level, so it's already kind of excited, and it goes to the third, and then it falls back down from the third energy level to the second energy level, it is going to release that red colored light as its photon as it falls back down. And that comes down as 656 nanometers, okay? A transition from the fourth energy level down to the second gives a wavelength of 486 nanometers. From the fifth energy level back to the second, it's 434. And then from the sixth energy level down to the second one, it gives 410 nanometers. So every colored line that you see here in these spectrums, those are actually individual transitions that are happening. So this one here, red, yellow, all of these transitions for helium, those are different electron jumps and falls that are happening. Okay? Hopefully that makes sense to you. What happens then is that, you say to yourself, well, that's a fun party trick. Like, why are we doing this in the first place? So here is where this becomes useful. what can happen is that we can actually take the wavelength of light that comes from that transition up, and then the photon coming out as the electron falls back down. And what we can do is we can actually calculate the energy it took to make that transition up and then fall back down. And if we know how much energy it takes to go up and then fall back down, what we can do is we can actually figure out how far away those electrons are moving and then how big of jumps they're making. Okay. Now, to calculate change in energy, or I'm sorry, we'll get to the calculation in a second. Energy is represented by delta E. So delta means change, if you remember from your math class, and then E is just for energy. And energy is measured in joules. And like I said, we will spend a lot of time talking about joules later on, but this is just kind of a bare bones discussion of that. What ends up happening is that when we do the work, if we find that there is more energy that you get out from your specific transition, the larger the electronic transition must have been. So if I get a lot more energy from my calculation and the wavelength of light that I get out indicates that, we will have a bigger energy change that happens. Okay, here is the equation you need to know. Like, if you get nothing else, this is what you need to know. The equation for calculating the energy for a given photon, and this is for one photon, is delta E, so your change in energy is equal to H times nu, and that's the same nu that we had in our previous lecture. Again, delta E is the change in energy. Nu is the frequency, and that is measured in seconds to the -1 or hertz. I prefer seconds to the -1 here. And then H is equal to something called Planck's constant. This equation and all of the variables, as well as H, are located on that equation sheet that I gave you in your booklet. So if you are worried about remembering this number, you don't have to worry about it. It will always be there whenever you take a test. Okay, so what happens is that if I know the frequency, I can figure out how much energy it took to make that transition up and down. Now, energy is measured in something called a joule. It's a very tiny unit that represents how much energy is in something. If you think about food, food provides you with energy, okay? 1 calorie of food. So if you think about one teeny tiny calorie, like I don't even know if you could eat one actual calorie. It's really hard to do. 1 calorie contains 4,180 joules. So if you think about it, it is a lot of joules that go into one teeny tiny calorie. So 1 joule on its own is actually pretty small, okay? We are going to be using this equation to figure out how much energy it takes for a transition to happen. Now, one thing that you should note in this situation is that if you have a higher frequency, you by default are going to have a higher energy because a constant number times a bigger number gives you a bigger energy value. So if I go back to this graphic here, and I see something that has 656 nanometers, okay? And I compare that to a photon that has 410 nanometers. It's counterintuitive, but the shorter the wavelength, the higher the energy of that light that's coming out. And I know that seems weird, but if you think about it, the math makes sense. So if I have a short wavelength, it means that my frequency is higher than if I had a longer wavelength. Remember our truck references. So what happens is the transition from the 6th energy level in this particular electron down to the 2nd energy level gives me a photon with a color that's a violet light and has 410 nanometers for its wavelength. Purple light has a higher energy than red light does, and it goes in rainbow order. So your lowest energy light is going to be red, then it's going to be orange, yellow, green, blue, and purple. And that's because if I have a longer wavelength like I do in red light, longer wavelengths are going to give me are going to give me shorter frequencies. And if we use this equation, a shorter frequency means I have less energy. So just keep that locked in your head. Red is lower in energy than purple is because of this equation. Okay, so we are going to go through a practice problem that I think is going to be really important to try. This one's not quite as straightforward as the other one. It's not quite as plug and chug as we like to call it, where it's very obvious. So I'm going to give you this problem. I want you to try it out. And then if you have any questions, take a look at the video and get your answer there. And then we can go over it. So the question for 1.2b is, what is the energy associated with 1 photon of light released at 656 nanometers, that's the red light that we talked about, when hydrogen is excited, producing a red colored line emission spectrum? Does the red line represent a higher or lower energy transition when compared to a green line? Okay, so practice that. If you have any questions, come to me in a Google Meet. Answers and work will be shown in the example video. All right, good luck.